Welcome to part one of the video podcast series having to do with acids and bases. We're going to go with very fundamentals in part one, and this is Ontario High School chemistry. So we're excited about that, and stay tuned. Want to look first at theoretical definitions. The first will be Arrhenius, or traditional, and this is the oldest of the acid-base definitions. So an acid is a substance that ionizes H+, which is a hydrogen ion, in aqueous solution. So here we have hydrochloric acid in aqueous solution, HCl, becoming H+, plus Cl minus, and an Arrhenius base, or traditional base, ionizes hydroxide ion, OH minus, in aqueous solution. So here we have NaOH becoming Ne plus OH minus. The next theoretical definition that we want to look at is the Bronsted-Lowry definition. And here an acid is defined as a proton, which is a bare hydrogen ion, H+, is a proton donor. And so now we write HCl plus H2O yields H3O plus, which is known as the hydronium ion, plus Cl minus. And this is a definition that came about because H plus does not exist independently in water. H plus always joins with a water molecule to form the hydronium ion. So the Bronsted-Lowry is a newer definition and a more correct definition of what an acid is. A base is then a proton acceptor. So in our next equation here, NH3 plus H2O becomes NH4 plus and OH minus. In this case, NH3, which we know as ammonia, is the Bronsted-Lowry base, and water is the Bronsted-Lowry acid. In the previous equation, HCl plus H2O yields H3O plus Cl minus. H2O is the Bronsted-Lowry base, and HCl is the Bronsted-Lowry acid. So here we have water acting as a Bronsted-Lowry acid in one reaction, and a Bronsted-Lowry base in another reaction, and we'll talk about what the term amphoteric means a little bit later in this podcast. The last of the theoretical definitions that we want to look at is the Lewis acid-base theory. In a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. For instance, H plus H2O yielding the hydronium ion. The H plus and the H2O form the hydronium ion because H2O provides both electrons in the bond between H2O and the H plus, and that's called a coordinate covalent bond, if you remember that term from earlier in the course. So H plus would be the Lewis acid, H2O would be the Lewis base. Now in the next reaction, we have the fluoride ion, F minus, joining with boron trifluoride to form BF4, 1 negative. In this case, the fluoride ion provides both electrons to join with BF3 to form BF4, 1 negative. So the fluoride ion is the Lewis base, the electron pair donor. Boron trifluoride is the electron pair acceptor. And the necessity of the Lewis acid-base theory or the Lewis acid-base definition here is because we have a reaction that doesn't involve hydrogen but is an acid-base reaction. So that's what that has to do with. One more example, H plus NH3 forms NH4 plus, and here again H plus is the Lewis acid, it's the electron pair acceptor. NH3 is the Lewis base, it's the electron pair donor, and again a coordinate covalent bond forms between the H plus and the NH3. So the other thing that you can see with this is that these sometimes a reaction fits more than one of these theoretical definitions, and you want to keep an eye on that. As we identify Bronsted-Lowry acid-base conjugate pairs, we look at our reaction. HCl plus H2O yields H3O plus Cl minus. HCl donates a proton so it's the Bronsted-Lowry acid. H2O accepts the proton, it's the Bronsted-Lowry base. H3O plus is the conjugate acid of H2O, which is the Bronsted-Lowry base, and Cl minus is the conjugate base of HCl, the Bronsted-Lowry acid. The definition that has the most meaning for us is the Bronsted-Lowry acid-base theory. And part of the Bronsted-Lowry acid-base theory are what are called acid-base conjugate pairs. And so if we look at the following reaction, here we have HCl plus H2O forms H3O plus and Cl minus. The acid conjugate base pair is HCl and Cl minus. The base conjugate acid pair is the H2O and H3O plus. So continuing to look at this reaction, we can identify the conjugate base of the acid because the conjugate base has one less hydrogen and one more negative charge than the Bronsted-Lowry acid. The conjugate acid has one more hydrogen and one more positive charge than the Bronsted-Lowry base. So you can see here the conjugate base of HCl is Cl minus. It has one less hydrogen. It goes from HCl to just Cl minus, and it has one more negative charge. The conjugate acid of water, which is the Bronsted-Lowry base, has one more hydrogen, H3O, and one more positive charge. It's H3O plus. Here is a problem for you to do. Identify the Bronsted-Lowry acid and base as well as their conjugates in the following chemical reactions. I'll ask you to go ahead and pause the podcast, work this out. The acid just identify with an A, the base with a B, the conjugate acid with a Ca, and the conjugate base with a Cb. So good luck, and we'll see you here in a moment. Welcome back. Let's take a look at your answers. We have NH3 is the Bronsted-Lowry base, H2O is the Bronsted-Lowry acid. The ammonium ion, NH4 plus, is the conjugate acid. It has one more hydrogen and one more positive charge than its base. And the OH minus is the conjugate base. It has one less hydrogen and one more negative charge than the Bronsted-Lowry acid. On the other reaction, we have H2O plus H2O forming the hydronium ion H3O plus and OH minus as the conjugate base. And since this is what would be called an autoionization reaction, we just pick one of the waters to be the acid, the other water then is the base. The hydronium ion is the conjugate acid, and the hydroxide ion OH minus is the conjugate base. When we look at acid-base conjugate pairs, once you've identified what the Bronsted-Lowry acids and bases are, what their conjugate acids for the base and the conjugate base for the acid is, we often will write these in what we call acid-base conjugate pairs. So for our first reaction, NH3, NH4 plus is the Bronsted-Lowry base conjugate acid pair. H2O, OH minus is the Bronsted-Lowry acid conjugate base pair. Again, the conjugate base to an acid has one less hydrogen and one more negative charge. The conjugate acid to a Bronsted-Lowry base will have one more hydrogen and one more positive charge. Our second acid-base conjugate pairs would be H2O as a Bronsted-Lowry base and H3O plus as its conjugate acid, and H2O as the Bronsted-Lowry acid and OH minus as its conjugate base. So those are acid-base conjugate pairs, and we'll keep going. Time for you to write some acid-base conjugate pairs. So here you have 6 substances. I want you to write the formula and charge of the conjugate bases of each of the following acids. So go ahead and pause the podcast, write the conjugate bases for each of these, and when you're ready to check your answers, resume the podcast, and we'll see how that looks. Welcome back. Let's check your answers. Remember, the conjugate base for a Bronsted-Lowry acid has to have one less hydrogen and one more negative charge. So for H2SO4, which is sulfuric acid, the conjugate base would have one less hydrogen, so it's HSO4, and one more negative charge, so it's HSO4 1 negative. For H3PO4, its conjugate base is H2PO4 negative. For HBr, it's Br minus. For HF, it's F minus. For HNO3, it's NO3 minus. And for HClO4, it's ClO4 1 minus. How'd you do? Okay, in this problem, we'll have you write the formula and charge of the conjugate acids given the following bases. So again, you'll want to pause the podcast, go ahead and write the conjugate base or conjugate acids of these bases that are listed here. And when you're ready to resume the podcast and check your answers, you'll know when to do that. Great. Welcome back. Let's check your answers. Remember, when you write the formula of a conjugate acid of a Bronsted-Lowry base, you need to add one hydrogen and one positive charge to the formula. So HPO4 2 minus, add a hydrogen and a positive charge to it, becomes H2PO4 1 minus. And H2PO4 1 minus is known as the dihydrogen phosphate ion. The conjugate acid of the iodide ion, I minus, is HI, hydrogen iodide or hydroiodic acid. For the carbonate ion, CO3 2 negative, its conjugate acid is the bicarbonate or hydrogen carbonate ion, HCO3 1 minus. The acetate ion, C2H3O2 1 minus, its conjugate acid is acetic acid, also known as ethanoic acid, HC2H3O2. For the hydrogen carbonate ion, HCO3 1 minus, its conjugate acid is carbonic acid, H2CO3. And finally, for the nitrite ion, NO2 1 minus, the conjugate acid is HNO2, which is known as nitrous acid. How'd you do? We mentioned earlier amphoteric substances, and an amphoteric substance is a substance that can act as either an acid or a base. It acts as an acid by donating a proton, which is a hydrogen ion, H+, or a base by accepting a proton, which again is H+. So examples, water is amphoteric. It can donate a proton to form the hydroxide ion, OH-, or accept a proton to form a hydronium ion, which is H3O+. Second example would be the hydrogen carbonate ion or bicarbonate ion, HCO3 1 minus. It can donate a proton to form the carbonate ion, CO3 2 negative, or accept a proton to form carbonic acid, H2CO3. So here is a problem for you to solve. Identify which of the following substances would be considered amphoteric. Now, what I'd like you to do is to pause the podcast, write down the ones that you think are amphoteric, and then when you're ready to check your answers, resume the podcast at that time. Good luck. Well, how'd you do? There are three of these substances that were amphoteric. The HPO4 2 negative is amphoteric. It can form either the dihydrogen phosphate ion, H2PO4 1 minus, or the phosphate ion, PO4 3 negative. Water certainly is amphoteric. It can form either the hydronium ion or the hydroxide ion. And finally, HSO4 1 negative will form either sulfuric acid, H2SO4, or the sulfate ion, SO4 2 minus. How'd you do? One of the last concepts we'll talk about here is that of strong acids and strong bases. And a strong acid is an acid that ionizes 100% in aqueous solution. For instance, hydrochloric acid is a strong acid. If you dissolve HCl in water, it will go 100% ionized to H+ and Cl-. Now, a quick note, the H+ does not exist independently in aqueous solution. It exists as H3O+ or hydronium ion. But for simplicity, these are often used interchangeably. You'll see it both ways in your college textbook, so you want to get used to that. So here is the strong acid, and the one recommendation we have, there are thousands upon thousands of weak acids. There are only a few strong acids. the best way to keep them separate, to know which are strong and which are weak, is just to memorize the list of strong acids. There are 7 of them to memorize, and then every other acid is considered weak. So that's our recommendation. So here is our strong acids list. HCl, HBr, HI, HClO3, HClO4, H2SO4, the asterisk there because only the first hydrogen ionizes 100% for H2SO4. The product of its first ionization, HSO4 minus, its conjugate base, is a weak acid that does not ionize 100% in aqueous solution. So only the first ionization goes 100%. And HNO3. If you memorize those 7 strong acids, you'll be in pretty good shape. Strong bases we define as those which ionize completely in aqueous solution to provide 1 or more hydroxide ions. And examples here, NaOH goes to Na plus and OH minus. Calcium hydroxide, CaOH in parentheses 2, goes to calcium 2 plus and 2 hydroxide ions. So when you have a strong base that has more than 1 hydroxide ion in its formula, it will ionize 100% for all the hydroxides. So unlike H2SO4, which just ionizes the first hydrogen 100%, for a strong base, if there are 2 hydroxides per formula unit, both of those will be ionized, not just 1. So something to keep awareness of. Here's the list of strong bases. All group 1 metal hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide, cesium hydroxide, rubidium hydroxide are considered strong. So remember those. And then there are 3 group 2 metal hydroxides that are considered strong. Calcium hydroxide, barium hydroxide, and strontium hydroxide. The one thing with those 3 group 2 metal hydroxides is they're not very soluble in water. You'll want to consider all other bases weak. Well, we are at the end of the video podcast at Ontario High School regarding acid-base definitions and acid-base conjugates and what are strong acids, what are weak acids. I want to leave you with a quote from the interesting comedian Stephen Wright. On the other hand, you have 5 fingers. I wish you well.